Hey, jumping back into chapter 21, we're going to cover sections F and G in this video, talking about the substitution method. So think back to differentiation uh, when we were differentiating something that wasn't just x. So if it was like a sine of x squared, we had to use the chain rule to handle that. This video is going to cover the kind of like the chain rule in reverse, and it's using a method called substitution. This is not guaranteed to work 100% of the time. Sometimes we're going to have to make decisions about what substitution to make, and it will not be obvious. It might take some trial and error. With practice, you'll get better at it. And when I say it's not guaranteed to work at all, there are other techniques to use, but we can at least, kind of cheat the system here a little bit. We know we're answering questions for the IB exam or also for the AP exam. So those questions are going to be designed often so that substitution is the way to go. So, it's something to definitely try. If you don't see a basic integral like we saw in the last video, something that's in the formula book, then substitution is one of the first things that you should be going for. So let's take a look at it, and I want to start off by referencing section F. Section F is integrating a linear function of x. So this one here, that's not linear, right? That's quadratic. So I guess a better example would be if it had said sine of, for example, 3x minus 2 or something like that. So section F is all about what to do when you've got a linear function of f. And my advice is not to even read the section. There's nothing worthwhile in this, honestly. Just use the substitution method. I don't know. You can read it if you want. Maybe you disagree with me, but we're moving on. This is a substitution method. So here we are. We're in section G already. What is going on here? Okay. So in the blue box, that's from our textbook. I've said it a few times before. The du over dx, it's not really a fraction, but you could kind of imagine canceling out dx's to get from there to there. And that's kind of the idea of what we're going to do here. Another way to visualize this, I've typed down below. We have, there's a lot going on here, I know. We've got a function, f, and it's not f of x. It's f of some other stuff with x. So it might be f of x squared. It might be f of 7x squared all divided by 8, or, could be anything. But if we can get, if we've got an integral where it's that function multiplied by, and this is key here, the derivative of the inside piece, then our answer will be the antiderivative of little f, so that's big F, of our inside piece. And this is what I mean when I say it's the chain rule in reverse, because if we were to differentiate big F of u of x, we would get the derivative of big F, which is little f, of u of x, and then we'd multiply by the derivative of u of x. That's kind of the plan that we're going for. This screen probably just did nothing but confuse you. I'm sorry. Let's just try to do one, and then we'll see how this works out. So this first integral looks pretty nasty. We said in the last video, if you've got a binomial raised to a power, you could just expand it, and it's true. One thing you could do here is you could raise this binomial to the power of 4 and then multiply everything by 2x plus 3, and you'll have a polynomial left over, and then you can integrate that term by term. The problem is that that's a lot of multiplication to do, and that's going to be pretty time consuming. So it would actually be faster to do this another way. Looking at the integral, I notice that 2x plus 3 is the derivative of x squared plus 3x. So what we do is we rewrite the original integral. Instead of x squared plus 3x, we're going to write u. So here we've got u to the power of 4. Then I notice that the derivative of u with respect to x, that's du dx. And the derivative of this right-hand side with respect to x is 2x plus 3. Therefore, du over dx is equal to 2x plus 3, and we can substitute that in for that, leaving us with, kind of canceling out the dx's, the integral of u to the 4th du. That's super easy. That's just power rule. The integral of u to the 4th du is just u to the 5th over 5 plus c. And then we replace our u once again with x squared plus 3x. And we've done it. I tend to write my workout a little bit differently. I go one extra step from here, and I actually solve for dx. So then I perform the substitution of, instead of x squared plus 3x, we write a u. And then instead of the dx, I substitute in there du over 2x plus 3, and then that 2x plus 3 and that 2x plus 3 would cancel, and then I would get integral of u to the 4th du. It doesn't matter how you prefer to structure it. The book does it, obviously, this way with du dx times dx, but I don't know, that method always made more sense to me. Let's look at a few more of these so we can hopefully get into the swing of things a little bit. So we're going to use substitution. So the trick here is we need to find a function and its derivative hiding within the integral. And sometimes it's easier to spot than others. So here it's pretty easy to see that if we let the denominator be u, then the numerator would be du dx. Right? Derivative of x cubed plus 2x is 3x squared plus 2. So that's the substitution we're going to have to do here. So we see that it becomes eventually the integral of 1 over u du. It's just algebra getting up to that point. Remember what we said a couple chapters ago. Calculus is easy, algebra is hard. So the challenge here is spotting what substitution to use and then just changing everything so that our new integral is entirely in terms of u instead of in terms of x. Anyway, from there it's pretty straightforward. Again, we know the integral of 1 over u du should be ln of the absolute value of u plus c, and then we substitute the u back for the x's. In letter B, it's a little less obvious what substitution to use. I don't immediately see anything being the derivative of anything else. My intuition, after many, many years of doing problems like this, is to let the exponent on the e be the substitution. And indeed, that's what we're going to do. Now, I don't like the way that they've written out their work. They're kind of inventing this 1/2 and this 2 here all of a sudden. Like, where did that come from? Sorry, negative 1/2 and negative 2, in fact. So let's talk about how we could come up with this one, thinking through it a different way. Whoops. So we had the integral of x times e to the 1 minus x squared dx. I say we should let u equal the exponent. Well, let's take the derivative then. So du dx is going to be equal to, derivative of 1 is 0, derivative of negative x squared is going to be negative 2x. And I said my method is I like to solve for dx. So if I do that, then I'm going to have dx is equal to negative 1 over 2x du. So let's do all that substitution and see what this integral can change into. So I've got integral of, let me just write e to the u, since that was kind of where I started from. And whatever, I'll write the x in for right now. But instead of dx, I'm going to write times -1/2, there's an x down there, du. And then look at what happens. That x and that x are going to cancel out. And now I've got e to the u times -1/2. Well, I can take that -1/2 and I can factor it out. -1/2 integral of e to the u du. And that's exactly what our book has here. However, the method of getting there is quite a bit different. I'm going to obviously strongly recommend my way of thinking about it because I don't see why it's obvious at this point to just invent a -1/2 and a -2 if you don't know that you're gonna, if that's going to be helpful. So I do not like the book's approach to many problems when it comes to substitution. All right, trigonometry. We know that cosine is the derivative of sine, but we also know that negative sine is the derivative of cosine. So there's going to be different options we might choose here, and some will be more successful than others. So let's take a look at these. Starting with the first one. Book says to use u equal cosine of x. And that might not have been the obvious choice to you. Maybe you were thinking, hey, I think I should let u be sine of x since the derivative of sine is cosine. The problem is that if you set u equal to sine of x and you actually follow the process through, you end up with an integral that has both x's and u's in it. So it just doesn't work. And sometimes this is part of the process of doing substitution. You need to just try something and see if it works. So if you try u equals sine of x, you'll find out pretty quickly that it was a bad choice, and then you'll try u equals cosine of x, and then, oh, that one works out. Great. Letter B, so we're integrating cosine over sine. By the way, that means that we're taking the integral of cotangent. Just wanted to throw that out there. If you wanted to integrate cotangent or tangent, neither of which are on the in the formula book, you would want to switch them out into sines and cosines and then perform a substitution. And in this case, setting u equal to sine would work out because then we'll have 1 over u du as our integral. I think I said in the last video, that integral shows up all the time. And it's already shown up twice in this video. So that's a very popular one. Please be on the lookout for it. Now you might have something like this, and this doesn't look very pleasant. There's only one function in there. If you try substitution right away, you're probably going to end up trying u equals sine of x, in which case we know that the derivative will be cosine of x. That's going to give us an integral of, I guess it'll be u cubed divided by cosine of x du, excuse me. Okay, well this again has u's and x's. I said in the previous problem that indicates we should have chosen a different substitution, although it's not obvious what it could have been here. We could, in this case, however, change cosines into sines, since we know that sine squared plus cosine squared equals 1. That means that cosine is going to equal the square root of 1 minus sine squared. And we know that sine, in this case, is u. So we could get it into that form. And that's not very helpful either. That's a complicated function. We can't actually integrate that directly. We don't really have any formulas for that. So maybe we should have tried something else from the very beginning. And this problem is not very obvious what you should try. But again, it's part of the process. Trial and error. Just try some stuff. So if we were to use trig actually first, sine cubed is the same as sine squared times sine. Sine squared, that's the same as 1 minus cosine squared. And then try a substitution where we let u equal to cosine of x. If u is cosine, then dx is going to be equal to du divided by negative sine of x. So we can see that that sign and that sign are going to cancel. We are going to have a negative factor to multiply through by, but really we can just rewrite that then as the integral of u squared minus 1. That's really easy to integrate. It's going to be u cubed over 3 minus u plus c. And then we substitute back because we don't want u's, we want x's. And this is a good time, I think, to advertise that there's plenty of websites out there that can help you if you get stuck on a problem when you're working at home. I like to use integral-calculator.com. I type in my function here. I verify that I've formatted it correctly here. You can do a definite integral later on, but you can just do that on a handheld calculator just as easily. Scroll down a little bit, and they give you not only an answer, but this is clutch right here, shows you the steps. And even this thing worked out the exact same trig substitution, the same u-substitution, and then kind of walks you through. I mean, it even has the easy stuff like, hey, use the power rule, solve the integral of 1 du. So some of the steps are a bit unnecessary, but this is wildly helpful, especially as we keep going through this. There's going to be some functions that are going to look pretty nasty, and at times you'll have no idea what to do, but this is a great way to help you start to recognize the patterns. Like even if you feel like you're using it all the time in the very beginning, if you start paying attention to how it tells you to solve particular problems, or how I tell you to solve particular problems, same idea. Hopefully eventually you'll start to pick up on the patterns and the repeated structures, and then you'll have better intuition in the future. So far everything we've seen has been pretty, well, I'm going to say it's straightforward, even if it looks complicated to you. Don't worry about that. Pretty much everybody who's ever studied this stuff struggles with substitution at first. But once you get used to it, you'll see that the ones we just did are really not that bad. Some problems, however, require additional steps or different ideas for what the substitution should be. So this one will demonstrate a problem with an additional step. So when I see a square root in an integral, my instinct tells me to let u equal the thing underneath the square root. That works out most of the time. So in this case, that gives me du dx is equal to 5, or I'll write du is equal to 5x, and then I need to get dx alone. So this is 1/5 du is dx. And then I'll go back and I'll rewrite my integral. So I've got a 1/5 coming outside, integral, still have that x there, that's weird, times the square root of u du. And yeah, that's a problem because I was unable to eliminate this x. There was no x showing up in my differentiation of u step over there. So what do? We can't take the integral of x du, at least not in a meaningful way for us right now. Well, the key is actually right over here, because if u is equal to 5x plus 1, that means that x is equal to u minus 1 divided by 5. So I just perform that substitution, and I put this in right there. So now I'm dividing by 5 already from the integral, and then I have another division by 5 in this substitution. So I'll write 1/25 integral of, now this will be u minus 1 multiplied by u to the 1/2. So that's going to be u to the 3/2 minus u to the 1/2 du. And then we're just going to integrate using the power rule. So I've still got a 1/25 multiplied by, this is going to be u to the 5/2 divided by 5/2 minus u to the 3/2 divided by 3/2. And then we distribute the 25 in, and we also substitute back, and that'll give us a final answer of 2 times 5x plus 1 to the 5 halves, all divided by 125, minus 2 times 5x plus 1 to the 3 halves, all divided by 75. And don't forget the plus c. I know I really should have had it in right there, but I didn't. Ooh. Really bad. Actually, you know what? It doesn't matter whether I put it in the brackets or not, because I'm glad I made this error so I could make this point. When I distribute the 1/25th and I multiply that by a constant, what is my answer? It's just a constant. So it actually doesn't even matter where that plus c goes. So anyway, that's an example of integration with an additional step where after you perform the substitution, you're still left with a pesky x inside the integral. The trick there is just to go back to your original substitution and rewrite it to get rid of the x. All right, now sometimes when you're doing substitution, you'll see right away, oh, I've got kind of two functions going on, and I see that one is the derivative of the other, or it's really close to it. Sometimes, like with the last problem, it's not really obvious where the derivative is hiding, and you're going to have to do something else. But oftentimes, it's just not clear. And unfortunately, there's no single rule that's going to work for every substitution problem. But that being said, the book suggests the following set of guidelines that you might want to try. And the first one I actually used in the previous example. So whenever we see the square root of a function, trying to set u equal to that function underneath the square root is a good idea. And the other four here are pretty decent ideas too. Now the good news is that most, I don't want to say all, I'm not sure, but most of the time that these fancier substitutions show up in an IB exam, they tell you use the substitution, or sometimes they'll say using the substitution or otherwise. So oftentimes they're gonna give you that little push, but I can't guarantee that that's the case. And if you happen to be studying for AP as well, they're not going to give you any of those hints there. You're going to be expected to know these like trigonometric substitutions. Okay, we'll do this one fast because it actually is just like the one we just saw. We've got a square root. We probably want to try setting u equal to the thing that's underneath the square root. But when that happens, there's going to be an x left over after the substitution. Notice that if u is equal to x plus 2, then that means that x is equal to u minus 2. So that substitution happens right there, and then we're able to integrate very easily. This one's a little bit tougher. We'd still try setting u equal to x squared minus 9, but that won't work. In fact, I'll show you why in a moment. In this case, since we have the format of the square root of x squared minus a squared, and in this case, a is equal to 3. This one right here. A is equal to 3. They want us to set x equal to a times secant theta. So x is equal to 3 secant theta, and that's exactly what they do. And then let's just see what happens. Now, it's not the most obvious choice in the world, right? If I hadn't shown you that chart a minute ago, you probably would have never thought to try this, but it's going to work. We're now going to take the derivative with respect to theta, and let's... Okay, our x squared is now 9 secant squared. Our denominator is 3 secant. And then dx is equal to just 3 secant tangent d theta, so that's going in there. The secants are going to cancel, so that's pretty cool. After that, we can, oh, and the 3's will cancel either, I should say. We can take out the 9, factoring out the 9 from inside that brackets. That comes out as a 3, leaving us with just secant squared minus 1. But secant squared minus 1 is, that's trig identity. Secant squared minus 1 is tangent squared theta. So then we take the square root of tangent squared, leaving us with just tangent, combining with this other tangent, gives us the tangent squared. And then I don't know how to integrate tangent squared. I'm not sure that I would have thought to, whoops, whatever, leaving that color change. I'm not sure I would have thought of this. To rewrite that as, again, back to secant squared minus 1, and then distributing through with the 3's, whatever. That's convenient, though, because we can integrate secant squared. We can integrate secant squared because we know that the derivative of tangent is secant squared, so the integral of secant squared is going to be tangent, and then that's just 3, so that's easy. That gives us an answer in terms of theta, but then we need to go back in terms of x. We know what x is in terms of secant theta up here. Secant is the reciprocal of cosine, so that means we know a relationship between x and cosine, and then we can draw in a right triangle. Since we know what the value of cosine is, we can therefore work out what the value for tangent is. You could have also done this using the fact that cosine squared plus sine squared is equal to 1, and then you could work out what sine squared was, and then work out what sine is, and then you could do sine divided by cosine to get tangent. Anyway, substituting all this stuff back in, wow, there's so much going on. This is so exciting. Finally, we get an answer in terms of x's. That incredible. If you wanted to try this problem using the original idea of letting u equal to x squared minus 9, you can start that off. But then you'll see that there's going to be some trouble with this integral, u to the 1/2 over u plus 9. I decided to try to do this on an online calculator because I was feeling pretty lazy. Now this is going to give me an answer in terms of u, which I would then have to go back and change into x's, but here we go. Okay, they gave me this answer. I haven't checked to verify that I could transform this back into the correct one, but I assume that I could. Let's see all the steps that they go through. They're doing another substitution now to get it into this form, and then they're using partial fraction decomposition to break this fraction into 2, and then integrating each of those. Looks like there's another substitution happening for w's. This is great. Don't you wish you could go through all these steps? No, probably not. So using the substitution suggested is probably the way to go. So if this problem had said, using substitution x equals 3 secant theta, or otherwise solve the integral, please use the substitution that they suggested. Okay, that problem was terrible. Many of the problems that involve these substitutions end up being terrible, but you know, just give it a go. I know I say this all the time, but if you want to get good at this, you got to practice. You got to do a whole lot of problems on yourself. Watching the video or reading through solutions isn't going to be enough, so please get out there, just dive in headfirst into some substitution problems and give it a go, and eventually, over time, you will, I promise, start to develop a sense for how to do these. I know it can seem very mystifying at first. I shared that concern when I was a student in high school as well, but you really do, it's just a feeling. You'll get this gut instinct developed over time, and that's true for integrals in general, because sometimes you need to use the standard formulas that are in the formula book. Sometimes you need to use substitution. Sometimes you need to use integration by parts. And when you get out there into even more advanced calculus stuff, there might be other techniques that you might learn. So it's really just you have to analyze each one on a case-by-case scenario, and one size doesn't fit all, but with time and with practice, you can start to get a good idea of what the more efficient approaches might be. Okay, I'm going to shut up now. So substitution, hooray, go practice, do the math.